Hi, everyone. This is not Brett Hall. This is Logan Chipkin. I am president of Conjecture Institute. And today I'll be speaking with friend of Conjecture Institute, physicist Vlatko Vedral. Vlatko is known for his contributions to quantum information theory, quantum mechanics, and quantum entanglement. And he has developed a novel way of quantifying entanglement and applying it to macroscopic physical systems. He's written several books, both textbooks and books for a popular audience to explain concepts in science. And today we'll talk about his latest book, which is Portals to a New Reality: Five pathways to a Future of Physics. Vlatko, thanks for joining me.
Thanks very much, and I'm very grateful for your support as well, and for hosting me today. I love your institute as well, by the way. It's a fantastic new development.
Thanks. Yeah, I appreciate that a lot. Yeah, full disclosure, two of our fellows are actually students of yours, and we're very
That's
happy
right.
to support them. Yeah.
Great.
Antonia and Samuel. Yep, absolutely.
Yes.
So let's talk about some of the ideas from your book. Now, before we get to any of the particular experiments that you lay out that can point us towards the next theory in physics, I want to talk about some kind of general ideas. You write about
Yes.
how quantum information theory is the way out of a lot of these blind alleys, as you describe them, that
Yes.
people, they try to unite quantum mechanics and general relativity, but they hit these brick walls. Now, I don't hear a lot, let's say, in mainstream reporting in the media about the tools of quantum information being useful to test the boundaries between quantum mechanics and relativity. So why do you think the tools of quantum information are so fruitful, and why do they not get as much attention as you think they might deserve?
It's a very good question, actually. Probably the answer is that it's a relatively new field in many ways. If you look at the basic ideas of quantum information, I think it's fair to say that theoretically, at least, they started in the late 60s. There was a few developments in the 70s. Probably in the 80s, we witnessed the biggest theoretical progress, at least. However, it wasn't maybe until the early 90s that people on the experimental side started to take these ideas more seriously. So I think it took a long time. It took about 2 or 3 decades for these ideas to actually permeate to the relevant experiments. And then, of course, they started to confirm various protocols that were proposed theoretically. Even that wasn't sufficient, by the way. Even the 90s were extremely slow. And I think the real genuine change, almost like a phase transition, took place 2000 onwards. And this is when people who were using macroscopic systems like Josephson junctions, for instance, superconducting systems, really started to show that you could test genuine quantum effects in these systems too. And because these were already solid state systems, I think the idea was taken seriously by various industries. All heavy industries are now involved. So I would say experimental progress has been really phenomenal in the last, let's say, 15, 20 years. And that's a real game changer. Because these theoretical ideas are fine, of course, and they're very exciting. Things like super dense coding in quantum communications, quantum cryptography, quantum teleportation. They were all theoretical ideas that I think excited many people, but I think it wasn't until experimental physicists got involved and started to verify these protocols that I think everyone realized that these tools are extremely useful. And I think they teach us a lot about quantum mechanics. So that's what's interesting to me. One thing is, of course, the experimental progress in trying to build a universal quantum computer, which would be technologically a phenomenal thing. But to a person like me, what's always interesting is, can we now use these new technologies that have been developed recently? Can we use them to test basic physics? So I think it's taken a long time, probably because of the lack of the right technology really to test some of these ideas. But you are right to point out that even on the foundational side, on how we understand quantum mechanics, probably the opinion is changing still relatively slowly. It certainly is changing because the experiments again are advancing, but obviously there are many domains where we still haven't tested these ideas. So I think people are still hedging their bets as to what quantum mechanics is really telling us about the universe.
Yeah, so that makes sense. Now, speaking of the kind of gap in some of the theoretical worldviews on quantum mechanics and related ideas in physics, you also write in the book about how everything is made of Q numbers and Q waves. Now, again,
Yes.
if you're following popular accounts of physics of quantum mechanics, I don't think you'll hear a lot about this. So, what exactly are these Q numbers? What does it mean that the world is made of Q waves? And again, why is this view not very commonplace, at least if you're a layperson reading articles and books about science?
It's a good question. Actually, that's one of those topics that's very hotly debated by various people, certainly physicists, philosophers, historians of science as well. Because at some point, quite early on in the development of quantum mechanics, we are probably talking maybe a definitive time was the 1927 Solvay meeting, and I think everyone was present there. Niels Bohr, Einstein was there, Heisenberg was there. Who's who in quantum mechanics at that time? Dirac as well, I think. And they were literally debating all of these different views that you could still hold credibly and try to account for all the quantum phenomena at that time. So remember, this was literally only 2 years after Heisenberg's revolutionary paper introducing, in fact, as you mentioned, Q numbers into classical physics to really upgrade things into quantum mechanics. And I think my feeling is that partly possibly due to the force of his arguments, possibly due to the huge charisma that he had. And you can even see this nowadays with various opinions. It seems to me Niels Bohr was seen as the winner of all of these discussions. So somehow the view that prevailed at that point was the Copenhagen interpretation, which is it's an okay interpretation to hold if you're really only able to confirm quantum effects in the microscopic domain. But as you progress and you really start to realize that quantum mechanics applies at larger and larger scales as well, and just think about this year's Nobel Prize in Physics. These are people who actually showed that the classical laws of how electricity propagates around electrical circuits are actually completely wrong, precisely because currents in electrical circuits can also exist in quantum superpositions. You really need to use Q numbers to even describe things that we learn in high school is completely classical, and Kirchhoff rules and all of these things that we learn, in fact, were shown ultimately in the 80s and 90s that they're completely wrong. You have to really use quantum mechanics. So it took a long time for quantum mechanics to leave the micro domain and go into the macro. So Niels Bohr simply said quantum objects behave in this counterintuitive and weird way, but ultimately the meaning is derived by us observers. So he put a special role for observers, and I think he thought of observers as classical objects. So he said, never mind that in a quantum system, you cannot measure certain properties at the same time, like a position and the velocity of the particle. Once an observer decides to engage, this observer then actually says which kind of information you will distill. Whether I measure a position or I decide to measure a momentum, the restriction is that I can't do both, but I can certainly choose as this classical system, which one to observe. So somehow there was this hybrid model of reality. Quantum systems are weird and unusual, but ultimately all of the meaning, all the relevant information is really circulated between classical observers like ourselves. And it took a long time, like I said, for certain people to start to change their mind and to start to challenge this picture of reality. So it seems to me it was easy to maintain it in the old days simply because no one really had any indication how far this kind of behavior would go. But now things are very different. Now we can see macroscopic systems being fully in superpositions, being entangled. And it seems to me there is a change now in how people think about quantum mechanics, but it's still extremely slow. You are right. I don't think you see many people promoting the views that I've been promoting.
Right. Now, you were talking about the early historical debates on quantum mechanics and whether observers should be themselves regarded as quantum and this sort of thing.
Yes.
You also write in the book about the differences between the Schrödinger picture of quantum mechanics and the Heisenberg picture. Now, is this at all related to what you were just talking about historically, or is this a totally distinct phenomenon?
I think it's very much related, and that's another. There is a very funny quote, but by Dirac, I think. Possibly even at that conference. I'm not quite sure. He was a man of very few words. But I think the quote is that he says, Copenhagen interpretation is fine if you need to pass Cambridge exams, undergraduate physics exams, but it doesn't really do a good job if you want to understand what quantum mechanics is all about. So it seems to me this pragmatic attitude, and I think, as you know, physicists are pragmatic ultimately. If we need to calculate something and make a prediction, we really try to take the simplest route that we can take. And it could be that that's also behind the philosophies that ultimately triumph, as well as now you're asking about the formalism. You're saying we have these two formalisms that are seemingly equivalent. They ultimately would make the same prediction in most cases. However, somehow the Schrödinger way of talking about things ultimately is how we teach quantum mechanics. Almost everywhere in the world. I don't think anyone follows the Heisenberg logic. The danger with that, and I think that's what I also discuss in my book, is that you have this picture where the only relevant quantity in the world is really the wave function, the state of the system. Schrödinger called it a catalog of information. So it's basically a list of all the amplitudes. These are the things that you have to square to get the probability that your system could possibly be in once you make a measurement of your system. And this view somehow tends to downplay the importance of the things that you ultimately do measure. So the question is, what is the status of the things that you ultimately measure, like the position or the momentum or the energy of your system? And it seems to me somehow, because of this pragmatic ease with which you can really calculate things, this is not true always, incidentally. I have 2 or 3 very nice instances in which the Heisenberg way is actually, I would say, exponentially faster. It gives you a result basically in a couple of lines, whereas I think Schrödinger picture would take a couple of pages of calculation. It's not always true, but I think in most cases, it is true that the Schrödinger picture is more efficient. However, then it seems to lead us astray a little bit, which is because this wave function is a highly delocalized object. People then frequently talk about quantum non-locality. And this is extremely misleading, because if you really think that quantum physics is genuinely non-local in the sense that you do something in one region and suddenly something changes at a distance, what Einstein called the spooky action at the distance. If you really thought that that's how quantum mechanics worked, then you'd immediately be in serious trouble as far as relativity is concerned. In fact, even special relativity you'd be in trouble with. Forget about general relativity. And I feel that many people who say that it's difficult to quantize gravity, they're mistakenly following this kind of Schrödinger intuition, or the intuition that's derived. Schrödinger didn't have that intuition, by the way. Schrödinger himself knew better. But somehow, if you follow this intuition in the wrong direction, in the Schrödinger picture, you might really believe that the two theories are incompatible because one is non-local and the other one is local. And this is where Heisenberg helps a great deal. That's why if you emphasize observables, the Q numbers, I really like Dirac's terminology, actually. Even though it was Heisenberg who introduced Q numbers, and that was the first defining paper in quantum mechanics 100 years ago, it was actually Dirac who realized what was really going on. And he was familiar with these kind of non-commutative algebras already from geometry. And it was easy for him to recognize what was going on. And actually he saw, even the uncertainty principle and all of the consequences of that. So somehow if you want to really demonstrate in a completely straightforward and simple way that quantum mechanics too is local in the important Einsteinian sense, then it seems to me Heisenberg is the right way to explain things.
Okay, understood. So far, basically, we have, in terms of your ways of viewing quantum mechanics, that is, shall we say, in the minority, at least for now. You
Yes.
have the fact that looking at it from a quantum information theoretic perspective is way more important than people realize. And we'll get back to information theory.
Yes.
The Heisenberg picture is more fruitful, let's say, than the Schrödinger picture, at the very least, with respect to noting that quantum mechanics is local, and that if you're going to unify quantum mechanics and general relativity, you need to respect the principle of locality.
Yes.
And then we have the fact that I think you had mentioned briefly that you can't arbitrarily have a demarcation between the quantum world and then when you have an observer, suddenly it's described by the classical world or C numbers or this sort of thing. That everything is quantum.
That's right. And actually, there is a beautiful way that you can see this in terms of information theory helps a lot because it's simply quantum information allows you to really encode and process much more information than classically speaking. And if you couple a quantum system with a classical system, it's really like trying to squeeze an awful lot of information through a narrower channel, which is the classical channel. And it's clear that you will lose. You cannot preserve all the quantum information in this way. In physics, for instance, we cannot preserve the symmetries that we build. So all the conservation principles, conservation of momentum, of energy, anything like that, including, by the way, the equivalence principle of general relativity that we may talk about later, none of these are possible if you really think of gravity as being classical. It's impossible to merge this classical information from gravity then with the quantum information from quantum systems.
I see. And since you brought it up, I was going to bring this up later, but let's talk a little bit about one of the big experiments of your book. And of course, now I'm talking about the BMV experiment, or the Bose Marletto Vedral experiment, because precisely it invokes concepts like quantum information and gravity, of course. So maybe just if you could give a broad outline of the motivations behind the experiment and how quantum information theory, what kind of role that plays in its genesis.
Yes, so I think that's an excellent example that uses a number of these quantum information principles. So it seems to me, you see, because on the Einsteinian gravity, of course, the theory of general relativity is still a classical theory. Classical theory in the sense that you don't have these Q numbers pertaining to all the properties. They're really just everything that's observable there is simply a real number. It's a C number. It's a classical number. And it seems to me that's why people don't necessarily see a big value in trying to reformulate general relativity in terms of information. So while this helps a lot in quantum information, many people would probably say, well, in gravity, it's almost self-evident what ought to be observable. And I think maybe that was part of the that was what was missing, maybe, to start to ask some of these questions. So the big question really is, if you have a massive object in a superposition of two different places, then the question is, how should gravity respond to that? Because classical gravity, of course, by definition of being classical, doesn't understand the Q number that pertains to this massive object being in two different places at the same time. And therefore, quite a few of my colleagues who think that gravity would somehow win this battle with quantum mechanics. So this is very much, again, in the spirit of Niels Bohr, thinking of gravity almost as being a classical observer, something that collapses these quantum numbers and distills C numbers out of them. So some people would say, well, classical gravity would have to decide which of these elements of the superposition it would respond to, but it would only respond to one of these elements at a time. So there would be some kind of collapse of this Q number. One of the outcomes would crystallize, and the mass would then suddenly localize itself in one position, and then gravity would just act on this as it normally does in general relativity. So what Chiara Marletto and myself wanted to test is exactly whether this is the right story, or whether gravity itself has the ability to actually communicate with quantum information. In fact, not just communicate, but fully transmit quantum information from one place to another. So that's, I think, that's where quantum information is important, because it seems to me that people who are not familiar with this way of thinking wouldn't necessarily think along these lines. It wouldn't necessarily occur to them to test these properties in this way. So when people talk about quantum gravity, incidentally, usually you think about particles that would transmit gravity. Gravitons, people call them gravitons. So the same as a photon transmitting the electromagnetic force, graviton is thought to transmit gravity. However, if you do a very simple analysis of the energies that would be required to test this kind of, or let's say how long you would have to wait for the gravitons to be emitted, these are experiments that are really orders and orders of magnitude away from anything we can do now. So that's why many people said, well, gravity may well be quantum, but actually we're never going to even be able to ultimately detect gravitons. Therefore, we might as well just continue to treat it classically. And again, quantum information helps here, because you don't have to think just at the level of gravitons. These Q numbers exist even at a much higher level where you could in principle detect them. So I can describe the experiment because it's a very simple experiment. You take one of these masses in a superposition, which, if gravity is quantum, would really affect the gravitational field simultaneously in two places at the same time. And this would now propagate in all directions, actually. But what you're doing now is you take another mass, which is a probe, and you put it also in a superposition of two different places. And what you're testing really is whether gravity, if you think of it as a channel, is able to communicate both of these positions of the first mass and imprint them onto the second mass. So in terms of Q numbers, what you are really doing is you're coupling a Q number that pertains to one massive superposition. You're coupling it to another Q number that pertains to another massive superposition. But your mediator now is the gravitational field, And unless this gravitational field also couples these two through Q numbers, you will never be able to execute this kind of transmission. And actually, it links beautifully to Schrödinger's ideas on entanglement. In fact, Schrödinger was all about entanglement being the characteristic feature of quantum mechanics. Schrödinger said, it's not just one of the phenomena in quantum mechanics, but making this joint superposition between two objects is actually the character. It's something that has absolutely no classical equivalent. So here the goal is really to test whether gravity is capable of making two separate superpositions in two different places entangled ultimately. And what we concluded, Sugata, Bose, and Chiara, and myself, is that unless gravity is also quantum mechanical, at least at the level relevant for this experiment, you will never end up having entanglement between these two masses. So that's like a witness of the gravitational degrees of freedom. And it's a far simpler experiment. It's an experiment that you could do in the lab in principle, rather than, requiring accelerators that cost a lot of money and need a lot of energy to generate to detect gravity.
Right. So that all makes sense. Now I'm thinking if the experiment, let's say, succeeds, and well, first let me just back up and kind of summarize the experiment. So the idea is, okay, according to the principles of quantum information, basically these are universal. The whole world, as you say, is made of Q numbers, and that must somehow include gravity. We don't necessarily know. We can talk about this later. Which elements of gravity are described by Q numbers, which are still somehow C numbers, whatever. C numbers are classical. Okay, but anyway, in this experiment, we have one mass, and it's in a superposition, and therefore its gravitational fields are also in a superposition. And then we have another mass that is also in a superposition, and therefore its gravitational fields are in a superposition. And then they interact in such a way that at the end, you make a particular measurement to see whether or not the two masses are entangled. And because their gravitational field was the only game in town in terms of what could have affected them locally, then it must be gravity itself that was as you said, the channel, the medium that transmitted the information such that they became entangled.
Yes, and entangled, maybe just even to add to that, to really clarify what this means, it really means that when you measure these masses ultimately, they will actually be found in the same respective position. So if you measure one mass in one location, the other one will be in the same corresponding location, and the same for the other. They will be super correlated, as Schrödinger emphasized. So somehow they will assume what you are really communicating is the state of these masses between each other, and it's gravity then that correlates these Q numbers that end up leading to an entangled state.
Okay, yes, thank you for that specification. So now it sounds like, the theoretical argument behind gravity necessarily consisting of at least some Q numbers, that is to say, it being capable of being in a superposition, capable of transmitting quantum information, of mediating entanglement. It sounds like this is theoretically uncontroversial. Now, of course, it still makes sense to run the BMV experiment, obviously.
Yes.
But now, having said that, let's just take for granted that indeed gravity consists partially of Q numbers. Do you have any concept of which aspects of gravity are quantum at all, or is that kind of like we're going to worry about that after we run the experiment?
It's a great question. Actually, as you know, and as I wrote in the book as well, I'm clearly on the side that gravity will pass this test. So I think it will be quantum mechanical. I don't doubt that entanglement will ultimately be observed. Obviously, if all the noise is controlled, and it's a very intricate experiment, it may take us a decade to get there. But I think ultimately gravity, I don't see any reason why gravity really should not pass that test. So to me, a far more interesting question is exactly the one you're asking now, because you're saying, well, what does that tell me then about what should I be doing with Einstein's gravity? So first of all, it would be a first piece of evidence that classical general relativity of Einstein is really wrong, and that would be great. It's falsified. But then the question is, how should we proceed now? So one, and it's not clear at all, by the way. So that's why someone like myself, who is really doing theory, and I can be well ahead of experiments. What you start to think then is automatically what would be then the follow-up experiments, where you could now start to discriminate between different quantum approaches. So yes, you've convinced people that gravity has to be quantum, at least at some level. So I can maybe take you through a few of these. The simplest way to think of, if you follow the electrodynamics analogy, you would simply take Einstein's gravitational potential, which is the metric of the field. That's the guy that tells you about distances between various points in space-time. And this field has 10 different components. So in the electromagnetic field, we only have 4 different components of the vector potential, and they become quantum numbers. That's the way we quantize electrodynamics. In gravity, if you really follow this prescription, that's called the canonical quantization. Canonical, presumably meaning the standard quantization. It's the first thing you would do. So basically, what you would do is take these 10 C numbers in Einstein's theory, and you would upgrade them into Q numbers. So one of these numbers would be the usual good old Newtonian gravity. That would be one of these numbers. It would also have to become a Q number. But the reason for 10 different numbers is because Einstein has in his theory the full equivalence between gravity and acceleration. This is the equivalence principle. So whichever way you accelerate, for instance, if you are rotating and you are getting centrifugal force, in Einstein's thing, these two could in principle be a component of the gravitational field. It would be indistinguishable under some circumstances from gravity. So you really need, Einstein saw that you need many more, it's not just a single parameter as for Newton, but you need 10 different parameters. So the simplest thing to do is really to quantize all of them. To explain the BMV experiment, you don't need to do that. You only need 2 components to explain that, and that does the job already. So that experiment is not necessarily forcing us to quantize them all. And so I think one follow-up set of experiments could be, how do we then test these other components? Are they also Q numbers? We would then have to think about experiments, let's say, on a rotating platform or things like that, where we would really entangle objects, but we would be using these different other components of gravity. That's one approach. Maybe that fails. Maybe that's not what gravity is all about. Some people, for instance, still stick very strongly to the original way in which Einstein thought about. I think Einstein changed his mind about this as well, ultimately, and he would have probably agreed with the canonical approach. But initially, he really thought about gravity as bending of space-time. And that's if you read popular accounts, and even the way we are taught general relativity frequently is like that actually gravity somehow is nothing but different rates at which time flows in different positions. And you can actually account for gravitational behavior in this way. So if you believe that it's really the space-time that's responsible for all of this, then it seems to me that what you should be quantizing is space and time themselves. And there are approaches to quantum gravity of this kind. It would be some kind of non-commutative geometry. So what you would be, it's very weird that if you assign quantum numbers to length, for instance, area, volume, they would all become Q numbers instead of C numbers. And then you would have this very counterintuitive thing, if you're coming from the usual Euclidean geometry, is that you cannot the same Heisenberg uncertainty would then apply, for instance, to the area and the volume. So it would be very funny that you could perfectly specify the area of an object, but then you would be clueless about the volume, in the same way as the position and the momentum work. So that's also possible, and various people are exploring this kind of directions. There are even probably what I would call more esoteric approach. These two would be probably conventional, and I think everyone could see some logic to this. The really esoteric or very radical, you may call them very radical approaches, would be that maybe gravity is not like other standard forces, like the other three forces that we have. Maybe gravity is a collective effect of some other, maybe it's an emergent phenomenon. So people are even, there are people speculating that maybe other quantum fields and the fluctuations of Q numbers of these other quantum fields are the leftover, this noise that's left over from the other quantum fields, if you add it all up, could actually account for gravity. So it's very interesting that in that case, you would even say, well, there is nothing to quantize there because gravity is not an independent thing. What you are really relying on is already other fields being quantum mechanical. So then I think the other two approaches that I described would not be the right way to do this. But discriminating all of these would require separate experiments. We couldn't do this with a BMV.
Right. Okay. So it sounds like, yeah, there are a lot of possibilities. Like if the BMV experiment succeeds, it's kind of it's a whole zoo after that.
Yes. Yes.
But although from a theoretical perspective, I would hope that maybe there are some constraining principles at work that could make your life a little bit easier, something like that. So
Yes.
before we leave the BMV experiment, I wanted to ask, you had said that there have to be two masses, but why could you not just use one mass and then run an interference experiment and see if its own gravitational field cannot interfere with itself?
It's actually a great question, and I think Feynman had this idea. There was a conference late 50s, I think, where lots of these discussions. This was really focused on quantum gravity, and I think Feynman's approach was. And there were other people at that time, Bryce DeWitt, probably John Wheeler advocated it as well, which was this standard, take the gravitational field to be these 10 components, and what it means to quantize it, really upgrade all of these 10 components to Q numbers. And actually Feynman and Wheeler and DeWitt even did some very simple calculations of relatively simple experiments. And that at that time, I think he had a question from someone, and I don't remember who this was, maybe Herman Bondi at that time, who actually asked a question of exactly what I was describing earlier, that he said, how would you know that gravity was really in a superposition and it wasn't just randomly affecting one branch of the superposition and then the other time the other branch? Because of course each of these experiments would have to be performed many times, and you would then get the statistics from all of these experiments. And I think Bondi was saying, how do you know that a simple classical stochastic model of gravity couldn't account for all of that? And then what Feynman described is having a massive object with a simple degree of freedom. It could be a spin, which you can put in a superposition of spin up and spin down. And then Feynman said, if it's spin up, you drag it in one direction. If it's spin down, you drag it in another direction. So he was describing how one would create this superposition. And basically then he said, now we need to understand, what does gravity do at this point? Is it really going to entangle itself, if you like, to both of these locations? Then it's very similar to Schrödinger's cat experiment. It's effectively Schrödinger's cat experiment. The difficulty, to answer now your question, why this doesn't suffice, is because what you're going to have to do in each of these interference experiments is you're going to have to bring these two different branches back into one place, which is what it means to interfere something. So you create a superposition, then you bring it back and you see the outcome. You see what happens when you bring them back. Now, the funny thing is that both outcomes, seeing interference and not seeing interference, are interestingly enough both compatible with gravity being quantum or gravity being classical. So neither outcome gives you any information, and that's interesting. So for instance, let me take you through one of these possibilities. Imagine you interfere the mass back and you really don't see any interference fringes. You just don't confirm any quantum effect. And now you say, what does that mean for gravity? Well, it could be that gravity is really classical and stochastic, and it disturbed the quantum superposition. The superposition collapsed, and that's why you don't see any interference. That's possibility A. But an even more interesting possibility, and again, that's what Schrödinger would have said, it could be that the gravitational field got entangled to the system. And now, when you interfere this entanglement stays, and that's actually what prevents you. It's simply decoherence that you created by entangling yourself to the gravitational field. So it's very interesting that if you manage to do things with one mass, it's certainly still an extremely challenging experiment. There's no question. And I think that's the first thing that people would try to do, obviously, before you attempt the full BMV. But somehow it really is ultimately inconclusive as far as this is concerned. And you can do the same if you see interference. If you see interference, you could say, well, gravity was classical, but it wasn't strong enough to disturb it. Or you could say it was quantum, but when you brought these things back, you brought back the two gravitational fields as well, and you actually interfered everything together, so no wonder you have interference. So even that outcome doesn't conclusively tell us anything, which is actually why Chiara and I proposed another mass in a superposition as a probe, and then you can definitely eliminate these possibilities and narrow it down to only one possibility.
I see. So it's almost like a Goldilocks situation. Not too quantum, not quantum enough. Okay, got it.
That's it.
And we should say, maybe we didn't specify this about physically what it means for something to be described by Q numbers. Tell me if I'm wrong, but to me, it's what everyone kind of intuits about what it means to be quantum, which is that, for example, velocity and position, that you can't measure them simultaneously, that sort of thing. So if gravity has these two, and I'm speaking very coarsely, of course, if gravity consists or partially consists of Q numbers, then there are aspects of gravity that can't simultaneously be measured as well.
Yes, exactly right. Actually, the nice thing to think about, and it's a perfect analogy with gravity. We can also discuss that. In electrodynamics, you could say the same thing about the electric and the magnetic field. So basically, the electromagnetic field has 6 components that you have to specify at every point in space. And classically, they're just C numbers. So it's not a problem to specify them at the same time. So you give the 3 components of the electric field in the X, Y, and Z direction, and the 3 components of the magnetic field, X, Y, and Z. Now, what it means to upgrade them to Q numbers is that you can no longer simultaneously, exactly the uncertainty principle that you now stated. You can't, they can all be Q numbers at the same time, but what that means is that you're not going to get a definitive outcome simultaneously from all of them. So if you know better the electric field component, then you are not going to know as well the magnetic field component. And the same story goes for gravity. For instance, if you take not 2 stationary masses, but you take 2 moving masses, there is an effect that's analog to induction in electrodynamics. So Faraday's induction, in which case you're going to have 2 components of the gravitational field. There will be one component as though the masses were static. So it's exactly like moving charge. You still have the static Coulomb, as we call it, Coulomb repulsion between charges, but now you also have moving currents, and the moving currents tend to attract each other, the moving conductors. So actually you have to worry about at least 2 different components of the electromagnetic field, and the same is true for gravity. And what these numbers being Q numbers means is that you can no longer specify exactly, if you know the Newtonian component really well, that means the induction component will be much less certain. So it's exactly the same story that would go here. Of course, this is providing that that's the right thing to quantize in gravity. And that's exactly, I think we're now almost starting to discuss the kind of experiments we would have to make in order to confirm whether this is the case.
Fascinating. Okay. Very interesting. Thank you for that. All right. So let's talk about at least one or two more experiments from your book. So going back, taking a step back from general relativity to special relativity.
Yes.
Yes. You talk about situations in which we have, let's say, atomic clocks in superpositions that are moving at different speeds. So naturally, if we have, for people who don't know, atomic clocks are some of the most precise clocks we have. And of course, they move at extremely rapid frequencies. And then if superposition is a quantum effect. So just walk me through that experiment and what would be the purpose of running that experiment, especially because, from a layman's perspective, I thought we had already understood how to integrate quantum mechanics and special relativity. So what's the significance of this experiment?
Yeah. You're right. I think that's a very good question, because you could say we have quantum field theory, and so quantum field theory would certainly agree with the predictions that I will now discuss. However, no one, interestingly enough, has tested it in that domain. And given that if you doubt already some of these things that have been then absorbed into general relativity, it's important really to take a step back and ask what does this mean even within the context of special relativity. And there's something interesting here to emphasize, which is another thing that you almost never hear anyone talk about. Relativity, obviously, because of the name, and as you said, tells us that many things are relative to how the observers move, how quickly you move. Your speed determines the lengths that you measure, the time durations that you measure. They are all subjective in that sense. I mean, they're objective, obviously, in your own laboratory, but they're very different to the measurement that someone else would have in another laboratory. What's never almost emphasized is the quantum states. Also, the states that people would ascribe to quantum systems are also relative, and that's extremely interesting. And I think these kind of experiments would be testing that. So again, people frequently say, oh, relativity is a very different theory to quantum mechanics, but actually, if you think harder about them, there are many common points which they do share. And it seems to me that if the two are merged together, if that really was a successful merger, quantum field theory, it's because of these commonalities that they have. So the experiment, to go back to the experiment that you started to describe, we know in relativity the famous twin paradox, which incidentally, as you know, is not a paradox. And in fact, our atomic clocks have confirmed this, and people took these clocks on various flights around the Earth and then compared them with the clocks that stay back. So basically, one of the counterintuitive consequences, or maybe that's the main one, is that if you have twins and one of them goes on a journey and comes back, then that twin is always younger, and by how much younger depends, of course, on the speed and the duration of this journey, is always younger than the twin that didn't go on a journey. And that's interesting, and it's precisely to do with the fact that they account for their time intervals very differently. So someone moving at a certain speed really perceives measures, not just perceives, but even measures with any apparatus, with any physics, if you like. Any physical theory should measure the same time. What I thought is interesting here, quantum mechanically, and no one has tested that, is that you don't need two particles to do that. You can actually take a single atomic clock, put it in a superposition. So these experiments are always very, very similar in spirit. You're always combining applying superposition to whatever the other theory is telling you, and you're asking, what the outcome would be. So now imagine that in these two locations, you only take the particle on a journey in you only take the clock on a journey in one of these locations and you bring it back. In the other branch of the superposition, the clock just stays where it was at the beginning. And now the situation sounds almost paradoxical, and it's very even difficult to describe with the common language because we're not used to these things. Now you bring them back to the same point. So now you really have a single clock, but the clock is in a superposition of being younger, showing less time, if you like, and older, showing more time. And now I was going to add at the same time. And you see, this is where this relativity of time comes in. There is a time in one branch for the clock. There is another time in another branch, but there is a third time, which is the time of an experimentalist like myself who is doing the whole experiment. And I have a clock telling me how long the whole experiment, there's nothing ambiguous about it. So you can already see that quantum physics itself would actually ascribe different states to these different situations. It's perfectly compatible with special relativity, but it still sounds very weird. And now, of course, you can make a measurement. You can ask the clock, how old are you? You can ask, what time is it really? Upon which quantum mechanics would say that randomly now, with 50-50 probability, you would get either a younger clock or an older clock. But the very fact that it can exist in a superposition of times sounds to me mind-blowing, and no one has tested it. So if you believe that something could go wrong with general relativity and quantum mechanics, it seems to me that it's also important to already test the special relativity case, because why not then? Maybe your intuition is telling you that something will go wrong in this case as well. It's certainly a very counterintuitive situation.
Yes, I remember reading that part in your book, and I'm also kind of surprised that this experiment hasn't been done. I mean, I don't know anything about engineering for experiments, so maybe it requires more advanced technology than I was aware of. But in terms of the logic of the situation and the physics of the situation, it's not terribly complex. This almost seems simpler even than the BMV experiment. And the BMV experiment's not terribly complex either.
No, you're right. Yeah, these are simple experiments, and they're all about, you see, it caters to another group of people who feel that time itself should deserve a more special position. So probably these are people who are challenging already even relativity, because in relativity we bunch space and time together. But there are people who think that time is more fundamental, and somehow space is an emergent thing. That's also a possible view. Lee Smolin, for instance, I think would be one of the physicists who frequently argues this way. So for him, I think it would be extremely important to test. And if you really think that time is more fundamental, then you should test quantum mechanics even within the domain where you're playing games only with time, not necessarily with space-time or even with gravity on top of that. Even before all of that, it's important to test quantum mechanics in this domain.
Right, but then on the other hand, you have, for example, the Page-Wooders construction and Sam Kuiper's work showing that time can be emergent in quantum physics. And then you have, I always forget if it's been shown in general relativity. I think Julian Barber has shown it for Newtonian mechanics. Is that right? That you can have classical mechanics without having reference to time, right?
That's right. That's right. These timeless pictures. And I think, again, a very similar discussion to what we had with BMV. We could have it here as well, because you could now ask, okay, let's say you do the experiment and it passes, and you really have a superposition of different times, and there is nothing really contradictory about it. And again, I'm betting on that outcome myself. Then you could still ask the question that you are asking. So what does this mean for time? And it seems to me both of these pictures where time is fundamental, but of course it has to conform to quantum superpositions. That's what the experiment shows. But you could also say, well, no, it's just part of a huge block universe. It's a static universe. Everything that will happen has already happened and is sitting in this static universe. that too is completely compatible with this experiment. So actually, if you want to test these two different realities, it seems to me you would have to go beyond what we are discussing now. I think you would have to think of more sophisticated experiments.
Right. And then we also had recently, and this takes us a bit afield from everything we've been talking about today. So I won't go too much into it, but Chiara Marletto and David Deutsch, both of whom are associated with Conjecture Institute, of course, recently worked on Constructor theory of time. I think the preprint is out.
Yes.
So if that work is correct, then in other words, time, it's not like you need to make time a Q number to loop it into our conversation, simply because time is an emergent phenomenon anyway. It's not associated with any physical variable position.
Yes, I love that paper, and I think it resonates very much with what I would. That's why I'm also advocating that we should quantize the field components. You are right. I think of space-time as a convenient fiction, if you like to call it like that. It's a grid that we introduce to make our calculations easier, but it seems to me ultimately it's not necessary. You could always phrase one field relative to another field, if you like. You can always do it in that way. You never really need to talk about space-time, but I think your life would simply be much harder when it comes to practical calculations, which is why I think we still stick to space-time. But it seems to me that it's more likely that it's an emergent entity rather than fundamental.
Okay, so last topic, if you have time, because it's related to this discussion of space-time. So, and I hadn't read a paper about this until I read your book, I must admit. But you and your colleagues Fitzsimons and Jones created a new formulation of quantum mechanics that basically integrates space-time into the picture. Can you tell me more about this?
Yeah, that's a nice one. You see that it's all of these things come out of. In fact, most of physics progresses in this way, that you're trying to understand the two theories that we've tested so well, and we know that some of their basic tenets will certainly survive in whatever comes next. So we have quantum mechanics. I don't think anyone doubts the superposition principle, really. Certainly up to a certain level, it's been tested. There is no deviation. In general relativity, things like equivalence principle, really well tested. And now the question is, of course, will these two survive? In what shape or form they will survive? Which is why most of the time, probably what we do in theoretical physics is we explore alternative ways of phrasing one and the same thing. You mentioned Page-Wouters as another construction that basically reproduces the basic quantum mechanics, but in a timeless way. So this one is in a very similar spirit. What we tried to do, Joe Fitzsimons and myself and Jonathan Jones did a beautiful set of experiments with nuclear magnetic resonance spins. The idea was really to think of to encode not just the state of the system at one given time, which is how you do quantum mechanics. So you give the initial state of the system at whatever time t0 when you start your experiment, and then you evolve the state forward in time. You have this Hamiltonian, which is the energy Q number that tells you how the state evolves in time. And then you can evolve it for as long as you like whenever you perform your next experiment. And then you can verify all of these things. So it's always the initial state, apply dynamics, get the final state, and do your calculations. So what we thought is that we could do it differently. We thought, what if the quantum states could actually stretch across time? So we don't just give it at an initial time, but we give it at the next time, the next to next time, and we stretch it across all relevant times. And we call the resulting object a pseudo density. Pseudo in the sense that when you do this, you actually get what previously in your state would be a probability, would be a number that's always non-negative, a number between 0 and 1. For us, when we apply quantum mechanics to temporal things in this way, could actually become a negative number. So your density, your state, behaves in all respects like in the Schrödinger picture, if you like. However, there is this very important deviation that you can no longer interpret certain numbers as probabilities because they can be negative. And the reason is really because what you're doing here is you're treating different instances of time as different subsystems. So normally what we do is when we have two different atoms, we think of the state as subsystem 1 and subsystem 2, but it's all taking place at the same time. Now you take a single atom at one time and the same atom at the next time, and you pretend as though these are two different atoms that pertain to these two different instances in time. It's a very kind of radical stretch, if you like, applying quantum mechanics even to the temporal domain, but it works beautifully. What surprised us is that you can really do everything in this picture. You can describe dynamics in this picture. And I think the punchline, and that's what you're alluding to, is that it automatically absorbs relativity because you are already giving all of these outcomes to all the measurements at all spatial locations and all the times. And since you phrase it already that way, whatever relationships exist between these space-time points are automatically part of your pseudo-density matrix description. What's really exciting, and we don't know how to do that, is whether you could emerge space-time. And I think that's maybe what you were driving at with your question. Could you somehow then, from this quantum mechanical state that stretches across space-time, could you even distill space-time as a grid that's basically an outcome of this? And I think that would be the ultimate vision of this formalism. Of course, we don't know if we can do it and if this is consistent, but it seems to me that this would be very nice to do.
That sounds very exciting. As we wrap up, and I definitely should have kind of maybe clarified this earlier while we were talking about it, but I just want to disambiguate between space-time, which is what we've just been talking about, and the gravitational field, which is what we were talking about earlier with the BMV.
That's right.
So correct me at any point if I'm wrong, but basically space-time is this grid, and as we know from relativity, general relativity, it can move about and it's not a static thing. But then the gravitational field is basically the way masses affect this fabric of space-time. Do I have that right?
Yes, that's exactly right. So somehow there is an intimate connection between the two. And the question, I think that's an interesting one. And again, how does one probe these things is a big question, and that goes well beyond the BMV experiment. Is really whether you take the space-time as fundamental, and that gives rise, let's say, to gravity ultimately, which is what I said Einstein originally thought. And in fact, many people learn general relativity this way, or whether you really think as the gravitational field as being fundamental. And that's the thing that ultimately leads in some emergent way to how we think of space-time and all the transformations in space-time. So which way the causality goes is completely unclear. And if we think of the field being fundamental, and that's the thing that's made up of Q numbers, then really somehow space-time becomes a convenient fiction. It's no longer fundamental. But I think, again, many people would argue against it, and they would probably go in the opposite direction.
Okay, very interesting. I have a lot more questions for you, but I'm wary of time. But anyway, we'll definitely talk again soon. So Vlatko Vedral, thank you very much. I really appreciate it.
Big pleasure. Thanks a lot.
Thanks, Vlatko.
Thank you.